Have you ever been completely amazed by an AI? Like you sit down, you type in a prompt, and you watch a large language model write this perfectly rhyming, highly creative poem about your dog in, I don't know, 3 seconds.
Yeah, and it's always so impressive the first time you see it.
Right. You read it and you think, wow, we are officially living in the future. But then, maybe like 5 minutes later, you give that exact same AI a really simple logic puzzle.
Oh yeah, the classic logic failure.
Exactly. Something a middle schooler could figure out with a pencil and paper, and you just watch it logically unravel.
It's completely wild.
It confidently gives you an answer that makes absolutely no sense, but it argues for it as if it's stating a universal truth.
Yeah, it really doesn't back down.
So if you are nodding your head right now, you are definitely not alone. And more importantly, you are going to want to hear what we are unpacking in this deep dive today.
It really is the defining paradox
Yeah.
of modern AI.
Mm.
We are seeing this staggering linguistic brilliance and at the same time, utter logical failure. And it's all wrapped up in the exact same interface.
Which perfectly brings us to our mission for today. We are exploring a groundbreaking state-of-the-art Gen AI paper from 2026.
It's a really fascinating one.
It really is. It's titled Structured Abductive-Deductive-Inductive Reasoning for LLMs via Algebraic Invariants. Now, do not let that title intimidate you.
Yeah, it's quite a mouthful.
It sounds like a lot, but what we are really talking about here is how researchers are giving AI this mathematical and philosophical scaffold to basically stop it from hallucinating logic.
Right. And I mean, the urgency of this research really comes down to application. We're moving past the era where AI is just this cool creative parlor trick.
Exactly. It's not just making dog poems anymore.
No, not at all. People are integrating these models into actual engineering workflows, medical research, legal analysis.
High-stakes stuff.
Very high stakes. For those applications, you simply cannot afford a hallucinated citation or a flawed leap of logic. You need to actually trust the reasoning process itself.
And right now, the sources we are looking at really highlight how shaky that trust actually is. There is this shocking statistic from Anthropic back in 2025 that really sets the stage here.
Oh, the faithfulness stat. Yeah, that one is eye-opening.
It blew my mind. So you know when you ask an AI a complex question and it spits out a quote-unquote step-by-step explanation of how it got the answer?
Yeah, the chain of thought.
Right. We all naturally assume we are watching it think in real time, but according to the data, those chain of thought explanations are only 25% to 39% faithful to the AI's actual internal computation.
It's incredibly low.
It is. When the AI gives you a step-by-step answer, the majority of the time, it is essentially guessing the answer first and then retroactively fabricating a plausible-sounding justification.
Yeah, the term researchers actually use for this is the curse of complexity.
The curse of complexity. I like that.
It fits perfectly because as the problems we feed into an AI scale up and become more intricate, the accuracy sharply degrades because of a really fundamental architectural flaw.
Okay, break that down for us. What's the flaw?
Well, large language models do all their processing in one massive chaotic pass. It is, by definition, an autoregressive generation loop.
Meaning it just predicts the next word.
Exactly. The system is designed to predict the next most likely word based on the previous words. And because of that design, it is basically generating ideas, attempting to verify facts, and drawing conclusions all simultaneously.
So let me try to visualize that. It sounds like trying to build a house without any blueprints, where you are laying the foundation, running the plumbing, and painting the walls all at the exact same time.
That is a remarkably accurate analogy, yeah.
You never even pause to check if the foundation is actually dry before you start putting up the drywall.
Right, because the AI just physically wants to keep generating text. It can't stop itself.
So the obvious question is, how do we fix that? Because you can't just type a prompt in all caps saying, please think harder and separate your steps.
No. Unfortunately, you cannot prompt your way out of an architectural limitation.
Right.
The researchers behind this 2026 paper realized they had to completely restructure the entire reasoning pipeline.
And they went way back in time to do it, right?
They did. To solve a cutting-edge computer science problem, they bypassed modern tech entirely and reached all the way back to the year 1878.
Wow.
Yeah, pulling from the philosophy of Charles Sanders Peirce. He proposed a tripartite model of inference.
Okay, let's unpack this protocol. What did Peirce actually argue?
He argued that human logic is not just a single monolith. It is composed of three distinct, irreducible modes of thinking, and each one is governed by totally different rules.
And the authors adapted this.
Yes, into what they call the ADI protocol. That stands for abduction, deduction, and induction.
Okay, so if we were forcing the AI to stop painting the walls while it pours the foundation, what does the very first phase look like?
Phase 1 is abduction. In the framework, they label this as L00, which stands for conjecture.
Conjecture, so just guessing.
Exactly. This is the pure hypothesis generation phase. Given a problem, the AI scans for patterns and makes an educated guess.
Like a brainstorm.
Very much so. Abduction is fast, creative, and heavily reliant on pattern recognition. In psychological terms, think of Daniel Kahneman's System 1 thinking.
Oh, sure, the fast, intuitive thinking.
Right. The AI is essentially saying, hey, based on my training data, here is a highly plausible explanation or solution.
But at this stage, it is really still just a guess.
That is the critical distinction here. The framework explicitly recognizes it as a guess. It assigns an absolute maximum reliability score of 35% to any L0 conjecture.
Only 35%.
Yep. The epistemic commitment, meaning the system's actual claim to truth, is mathematically 0 at this point. It is merely flagging an idea as worthy of investigation.
Which is so different from how standard LLMs work.
Completely different. The fatal flaw of a standard unfiltered LLM is that it treats these 35% L0 conjectures as if they were 100% established facts.
Right, and then it just builds its next sentence on top of them.
Exactly, which leads directly to the hallucination spiral.
So, okay, the AI generates this 35% guess. But since we know it's just this autoregressive text generator that desperately wants to keep talking, how do we stop it and force it into phase 2?
Well, the framework basically operates as an external symbolic system running right alongside the LLM.
Like a chaperone.
Kind of, yeah. The language model handles the natural language generation, but this external scaffold interrupts the process, captures the output, and cracks the logical state.
Oh, that makes sense.
So once that L0 conjecture is captured, the framework forces the system into phase 2, which is deduction, or L1.
Okay, so what are we deducing here? Are we trying to prove the guess is true?
Actually, no. And that's a common misconception. Deduction in this specific context is strictly about proving that the hypothesis does not contradict established facts or constraints that the system already knows.
Oh, interesting. So it's just checking for obvious errors.
Right. It is about substantiation, not absolute proof. We are basically running the guess through a logical filter to catch any hidden contradictions.
And if it passes?
If it passes that filter, it gets promoted to an L1 substantiated claim.
Okay, but it still hasn't been tested in the real world yet.
Which is exactly why we need phase 3, induction, or L2.
And what does that entail?
This is the corroboration phase.
Yeah.
Here, the system actually requires empirical validation against real-world data.
Like running an actual test.
Exactly. That might mean running a block of code, checking an external database, or testing predictions on a held-out data set.
Got it.
And there's a very strict rule at this L2 stage. Every single corroborated claim must carry an explicit scope constraint.
A scope constraint? What does that mean in practice?
It means you cannot simply declare, this solution works. The system forces the output to say this solution works specifically under these exact conditions.
I love that. I want to ground this in reality, though, because the paper provides a fantastic worked example regarding a database retrieval system.
Oh, yes, the context window example.
Yeah, let's trace how a real AI navigates these 3 steps with that example.
Sure. Let's assume you are using an AI agent to optimize a massive database retrieval tool. During the abduction phase, that L0 conjecture, the AI looks at the performance metrics and guesses, hey, if we expand the context window from 4,000 tokens to 32,000 tokens, it will improve the answers.
Which, honestly, on the surface sounds entirely reasonable. I mean, more context usually means the AI has more information to draw from, right?
It's a very strong guess. It makes logical sense. But the external framework catches it and pushes it into the deduction phase, L1.
To check for contradictions.
Exactly. It checks that 32,000 token hypothesis against the system's known constraints. And it immediately finds a previously validated rule.
What rule was that?
For this specific database, the relevant documents have a long-tail distribution, meaning the most important information is usually found early on in the documents.
Oh, okay.
Because of that, accuracy actually plateaus at 16,000 tokens. The 32K hypothesis actively contradicts a known systemic constraint.
Wow. So the framework catches the hallucination before the AI can deploy a bad configuration.
Exactly. The hypothesis is rejected. And that forces the AI to refine its guess.
So what does the AI do then?
The AI adjusts the claim. It says, okay, a 32K context window improves accuracy specifically for multi-hop queries.
Okay, and for anyone unfamiliar with the term, a multi-hop query is basically when you ask a question that requires finding one piece of information and then using that information to find another.
Right, exactly.
Like asking,
Mhm.
who is the CEO of the company that makes this specific product? You have to hop from the product to the company and then from the company to the CEO.
Spot on. So that refined hypothesis about multi-hop queries passes the L1 logical check because it doesn't contradict the general plateau rule.
Because it's a specific exception.
Right. Now it enters the induction phase, L2. The framework tests it empirically. It runs a benchmark simulation and observes that the F1 score jumps from 0.72 to 0.81.
And just to clarify, an F1 score is a metric that balances precision and recall, right? It isn't just about how many right answers the AI got.
That's right.
It also penalizes it for false positives or missing relevant data entirely. So it's a much stricter measure of accuracy.
That is correct. And because the benchmark yielded a tangible, measurable improvement in the F1 score, the hypothesis finally becomes an L2 corroborated fact, complete with its explicit scope constraint.
That is just such a remarkably structured way of thinking. But as I'm listening to this, a pretty glaring logical hole jumps out at me.
Okay, what's that?
Well, if the AI is the entity generating the initial hypothesis, what is stopping it from just hallucinating the verification?
Oh,
Because we already established it suffers from a massive overconfidence problem. If it comes up with a bad guess, why wouldn't it just generate fake logical constraints to pass its own test?
it's a great question, and the authors of the paper anticipated that exact vulnerability.
Oh, they did. Good.
Yeah, they addressed it by implementing a strict structural rule known as the transformer mandate.
The transformer mandate. Sounds like a sci-fi movie.
It really does. But the mandate simply states that the entity responsible for finalizing a decision must be entirely external to the generation loop.
So it literally can't grade its own homework.
Exactly. An LLM is permitted to propose ideas and it can gather potential evidence, but it is physically restricted from ratifying its own conclusions.
That makes so much sense.
Right, because if a system allows an AI to validate its own outputs, it creates an infinite feedback loop of misplaced self-confidence. The verification mechanism must be anchored to independent external constraints.
So the external framework is acting as this brutally strict teacher, just tracking every single claim.
Exactly.
And the paper details how this external teacher tracks the claims using epistemic layers and formality levels. How do those two metrics actually interact?
Well, we've already covered the epistemic layers L0, L1, and L2.
Right, the journey from guess to verified fact.
Exactly. So parallel to that, the framework evaluates formality, which ranges from F0 to F3. Formality measures the actual rigor of the evidence itself.
Okay, break down those levels for us.
Sure. An F0 claim relies on anecdotal or informal authority, and its absolute maximum reliability is capped at 70%.
Got it.
F1 involves structured data, like explicit logical trade-offs. That's capped at 85%. F2 requires empirical load tests or established benchmarks, capped at 95%.
Okay, and the top level.
Finally, F3 represents formal, machine-checked mathematical proofs, which are capped at 99%.
Wait, I have to pause there. If a machine-checked mathematical proof is the gold standard of logic, why does it cap at 99% instead of 100%?
That is a very perceptive question. It's because even formal mathematical proofs rely on software-based proof checkers.
Oh, right.
And those proof checkers were written by fallible human developers. There is always a non-zero margin of error in literally any computational system.
That is incredibly rigorous.
It is. But the true rigor of this framework is revealed in how it synthesizes these scores using the dual ceiling constraint.
The dual ceiling constraint, how does that work?
To determine the final reliability of any claim, the framework maps the epistemic layer against the formality level, and it is forced to take the absolute minimum of the two.
Okay, let me make sure I follow the math on that. Say the AI generates an L0 conjecture.
A complete guess.
Right, a guess that we know is capped at 35% reliability. But say it manages to express that guess using highly formal F3 structured mathematical logic.
Okay,
The framework looks at both numbers. It sees 35% for the guess and 99% for the math. Because it takes the absolute minimum, the final score is still capped at 35%.
Exactly. It prevents the AI from using complex academic jargon to camouflage a really weak premise.
Wow. That leads directly to a detail in the paper that absolutely blew my mind.
0.39 cap.
Yes. Going back to that anthropic statistic we discussed earlier, the fact that current chain of thought faithfulness is at best 39%.
Right, the massive disconnect between the internal computation and the generated text.
Yes. Because researchers know the AI is so unfaithful to its own logic, the framework explicitly caps any LLM-generated evidence at a formality level of F1.
Which normally allows for up to 85% reliability.
Exactly. But under the dual ceiling constraint, the framework takes the minimum between that 85% and the AI's known faithfulness score of 39%.
So it instantly drops.
Yes, which means, straight out of the box, this system mathematically caps any unsupported AI logic at a reliability of 0.39.
It is so strict.
It is. It essentially tells the LLM, look, until you prove this with external data, I am mathematically required to assume you were just making things up. It mathematically enforces skepticism.
And it is a profoundly necessary layer of friction, And the framework actually tracks more than just the type of evidence. It tracks time.
Oh, really? How so?
Information within this system goes stale. Every piece of evidence receives a valid until timestamp.
Oh, that's smart.
Yeah, informal observations expire rapidly, while rigorous empirical tests hold their validity much longer.
That makes total sense.
And at the end of a reasoning session, the framework generates a design rationale record, or a DRR.
Okay, what is a DRR?
It provides a fully auditable, transparent trail detailing exactly what was guessed, what was logically checked, what was empirically proven, and exactly when each piece of evidence expires.
The structural elegance of the DRR is just impressive. But this raises a pretty massive logistical question for me.
Okay, let's hear it.
If I am building a complex system and the AI is chaining together dozens, maybe hundreds of these steps, hypothesis, constraint check, empirical test, new hypothesis, how do you actually calculate the final reliability score of the entire project?
Yeah, that was the core mathematical hurdle the researchers faced. How do you quantify the certainty of a massive interdependent chain of reasoning?
Right.
To solve this, they introduced 5 algebraic invariants, which they collectively call the gamma quintet.
The gamma quintet.
Yeah. But the crown jewel of these invariants, the one that fundamentally alters how we evaluate AI, is the WLNK bound.
WLNK.
Yes, it stands for weakest link.
The weakest link. Okay, here is where it gets really interesting. Let me try an analogy to explain why this is such a departure from how AI currently evaluates itself.
Go for it.
Imagine you have this really complex bomb in front of you, right? And you have to defuse it in 3 sequential steps.
Okay, high stakes.
Very high stakes. You are 95% confident you know which wire to cut for step 1. You are 85% confident in step 2.
So pretty good.
Right. But for step 3, you are only 40% confident.
No, that's a problem.
It is. Now, if you ask a standard AI to evaluate that plan, it will just average the confidence scores. It will calculate 95 plus 85 plus 40 divided by 3 and happily inform you that you are 73% likely to survive.
Which is terrifying.
It is, because logic dictates that you are only as safe as your weakest step. If you only have a 40% chance of getting the last step right, your overall chance of surviving is exactly 40%. Averaging your logic will literally get you killed.
That analogy perfectly illustrates the danger. Using an arithmetic mean to judge a chain of logic is fundamentally flawed because a single, glaringly weak premise just becomes diluted across the average.
The danger is hidden within the aggregate score.
Exactly. The WLNK invariant mandates that no inference chain can be considered more reliable than its least reliable premise.
So how does that actually play out in a coding environment? If the AI is writing a program, where does an averaging system actually fail?
Let's examine a 3-step deduction an LLM might make while, say, writing Python code.
Okay, yeah.
Step 1. Python's global interpreter lock, the GIL, prevents true parallelism.
Okay, that is a well-established, highly verifiable fact regarding how Python manages memory.
Right. So the framework gives it a high reliability score of 0.95.
Makes sense.
Step 2. Therefore, CPU-bound tasks cannot benefit from threading. That is a completely valid logical deduction stemming from step 1. The framework scores it at 0.85.
So far, the AI is making total sense.
But then comes step 3. The AI states, therefore, all Python programs should use multiprocessing instead of threading.
Oh, wow. The framework flags this as a massive, fatal overgeneralization, right? Because it completely ignores I/O-bound workloads. For anyone listening, an I/O-bound workload is when your program spends most of its time just waiting for something else to happen.
Right, like waiting on a network request. processed.
Exactly like waiting to download a file from the internet or waiting for a database to respond.
Hmm.
During that waiting period, the CPU isn't doing any heavy lifting, so threading actually works perfectly fine for those tasks because the threads can just take turns waiting.
Exactly.
Concluding that literally everything needs multiprocessing is a huge logical leap.
It's exactly the problem. And because of that leap, the framework assigns step 3 a reliability score of only 0.40.
Ouch.
Now, if you evaluated this using a traditional averaging method, the overall argument would score a 0.73.
That's crazy. The system would just rubber stamp the logic as moderately reliable, and a developer might deploy highly inefficient code.
Because the two strong facts completely mask the terrible conclusion.
Right.
But under the WLNK invariant, the reliability of the entire chain is instantly capped by the minimum score, 0.40.
The weak link drags the whole argument down.
Yes, surfacing the logical flaw immediately. And if we connect this to the bigger picture, what makes this paper so robust is that the authors didn't just invent this weakest link concept to make their code run better.
They didn't just guess it.
No, they justified it through what they call a quadruple triangulated approach. They proved it using 4 completely independent fields of study.
Let's break those down because this isn't just computer science we're talking about. It's deep theoretical math.
It is. First, they rely on algebraic T-norm theory, specifically the Gödel T-norm. This area of mathematics deals with continuous idempotent variables.
Whoa, let me stop you right there. Idempotent. That is a heavy academic term. What does that actually mean in the context of logic?
Fair enough. An idempotent operation is basically one where applying it multiple times doesn't change the result beyond the initial application.
Can you give an example?
Think about addition in math. If you add 2 volumes of water, you get a larger volume of water. It compounds.
Right.
But logic doesn't compound that way. If a statement is true, and you combine it with another statement that is also true, the result is just true.
You don't get a double true.
Exactly. The Gödel T-norm mathematically proves that when dealing with these non-compounding logical variables, the only mathematically sound way to combine them is by taking the minimum value.
That makes perfect sense when you put it like that. What are the other 3 pillars?
The second is possibilistic logic, developed by Dubois and Prade. They established that when you chain uncertain events together, the certainty of your final conclusion can never exceed the certainty of your least certain premise.
So it acts as a bottleneck.
Precisely. Third, we have actual empirical AI measurements from recent studies. Those confirm that an LLM's chain-of-thought accuracy actively degrades based on its weakest logical step.
And the 4th.
And finally, the algebraic formal specifications of the Gamma Quintet itself. 4 separate disciplines, all converging on a single, undeniable truth. Logic is strictly bounded by its weakest link.
I mean, the theory is beautiful, the math is flawless on paper, but, as anyone who works with software knows, theory rarely survives the first encounter with a compiler.
Oh, absolutely true.
How did the authors prove this framework doesn't just immediately break when you actually try to write the code for it? You have floating point errors, edge cases, infinite loops just waiting to happen.
Well, they validated it through property-based testing, or PBT.
PBT. How is that different from normal testing?
This is a massive step up from standard unit testing. In a unit test, you give the program specific inputs like, 2 plus 2 and check if it outputs 4.
Right, very straightforward.
Property-based testing is totally different.
Yeah.
You define universal rules or properties that must always hold true. For example, no matter what 2 positive numbers I add together, the result must be larger than either individual number.
Oh, I see.
The authors defined 100 of these mathematical properties and 16 fuzz tests, and then programmatically generated over 100,000 random edge cases.
100,000?
Yeah. They threw deep logical chains, diamond-shaped dependency graphs, and mixed topologies at the system just to ensure the algebraic invariants never failed.
With 100,000 randomized tests, something had to snap. Did it catch any major flaws?
It did catch failures, but the nature of the failures was really revealing. The authors included a great anecdote about testing the state machine that manages the epistemic layers.
What happened?
They wrote a standard reachability property. Every phase of the system must eventually be able to return to an idle state. But the test kept failing on a specific state called operation. The system would reach operation and just freeze.
So there was a bug in the code.
That was their initial assumption, yeah. But upon an investigation, they realized the code was doing exactly what it was supposed to do.
Yeah.
The bug was actually in their own mental model.
Wait, really?
Yeah. The operation state represented a finalized, deployed decision. It was intentionally designed to be terminal. They had a subconscious, undocumented assumption that didn't match the mathematical property they had written.
Wow.
The PBT didn't just stress test the code, it actually forced the developers to be completely transparent about their own design assumptions.
Which is incredibly poetic because forcing transparency and honesty is exactly what this framework is designed to do for the AI.
Exactly, it's a perfect parallel.
This is clearly a massive leap forward, but in the spirit of the framework itself, we need to maintain our skepticism.
Always.
Let's look at the boundaries. Where does the soda paper admit it still has limitations?
The authors are remarkably upfront about the constraints. Foremost, you cannot use this protocol with a simple, single-pass LLM prompt.
So no standard chatbots.
Right. If you just open a standard chat interface and ask a question, this framework cannot run. It strictly requires a multi-turn interaction or a complex multi-agent architecture where different components are actively managing the abduction, deduction, and induction phases.
And that introduces significant computational overhead and latency, I imagine.
A lot of overhead, yeah.
Which means you can't just slap this onto a consumer app and expect it to be fast and cheap. What else?
Those exact ceiling percentages we discussed, like capping L0 conjectures at 35% or capping F0 formality at 70%, those are currently highly educated defaults.
They aren't hard mathematical laws yet.
Exactly. They are policy decisions based on observation, not empirically calibrated absolutes. Different industries or domains might require adjusting those weights.
That makes sense.
Furthermore, while the mathematical integrity of the framework was heavily tested, it has not yet been fully evaluated against massive, dedicated logical reasoning benchmarks like zebra logic. That is definitely the necessary next step for this research.
So let's zoom out and look at the bigger picture here. What we are witnessing is a fundamental paradigm shift in how we build and interact with artificial intelligence.
It really is.
We are moving away from treating these massive text generators as omniscient black boxes that we blindly trust just because they sound confident.
Right, because confidence does not equal competence.
Exactly. We are acknowledging that they are fantastic at generating creative guesses, but structurally terrible at proving them. By building these external auditable scaffolds, by forcing the AI to separate its conjectures from its facts, we can actually begin to rely on its logic.
It represents the maturation of the field, really.
Yeah.
We are transitioning from asking, look at this incredible magic trick the AI can do, to demanding, show me the verifiable mathematical proof of why you made this specific decision.
And that matters to you, whether you are a software engineer building the next generation of enterprise AI tools, or simply someone trying to navigate a world increasingly flooded with AI-generated answers.
Absolutely.
Understanding how a machine arrived at a conclusion is now officially more critical than the conclusion itself. If the AI cannot show its math, if its reasoning cannot survive the scrutiny of the weakest link bound, it isn't giving you an answer. It's just writing you a poem.
A very articulate, heavily hallucinated poem.
Exactly. So I want to leave you with a final thought to mull over. The researchers proved, mathematically, philosophically, and empirically, that an AI's logic is fundamentally bounded by its weakest link, not its average confidence.
Right.
But think about your own brain. How often do human beings rely on the arithmetic mean in our own heads?
That's a scary thought.
It is. Do we let two incredibly strong pieces of evidence blind us to the one glaringly weak assumption in our daily decision-making?
We probably do, more often than we'd like to admit.
Yeah. In our relentless rush to fix the machines, are we actually holding AI to a higher, more rigorous logical standard than we hold ourselves?